Hello. Okay, it's on. Good. Okay, thanks a lot for coming. And so today I'm going to talk about learning simulation, which for many years has been sort of a vehicle for. Well, actually, I'm not sure which way it goes. Maybe I think it's a vehicle for us, my team, advancing some of our methods on graph neural networks. But maybe the graph neural networks are the vehicle that's advancing learning simulation. I'm not sure. They're cooperative. Anyway, so what I'm going to do is I'm going to show you how we made neural networks generate these types of videos up here. That's most of what I'll discuss today, and I'm going to sort of make an argument for why machine learning and learning simulation using machine learning is a good idea for all the sciences and engineering. And I just want to start. I'm presenting on behalf of all my collaborators. I think I probably left a few people out, but you can ask me. I can send you papers and direct you to people here if you're interested in knowing more about some of the work. Okay, so the first thing I want to start with is to impress on you that simulation as a tool is crucial at pretty much every scale of science and engineering. So from inside particle detectors and the software that they use to process the observations they're making inside at CERN and LHC, all the way up to like molecules and fluids and rigids and structural mechanics of, I think this is a bridge or something. I don't know what that is actually. Traffic, weather at the global scale, and even larger up to, my pointer went out, and that means I probably can't advance it. All right, well, weather, even solar systems, and up to the largest structures in the universe, galaxies, and even larger. So yeah, this died. It's too bad. Just give me 1 second. Let me see if I can flip the batteries around and play that game, get a little extra juice. We'll see how long it lasts. Okay, but before we kind of get into all this stuff, I want to start by saying, what is simulation? So I've worked on learning simulation for a long time, but when I was preparing this talk, I started to think like, this word simulation is sort of, it means a lot of different things to people, and different communities sort of mean, different things by it. So let's kind of try to bring our understanding, our kind of foundation of what we're thinking about together. So the first thing I did was I went to Wikipedia and I looked up simulation. And this is what the first paragraph said. And I want to call your attention to a few things. So first, it's the imitation of a real world process. It requires the use of models. Nope. Okay. What's that? All right, I'll try it. Thanks. Very cool. Thank you. Sorry about this. Thank you. All right. It involves the evolution of the model over time. And crucially, computers execute the simulation. Okay, so bear these in mind for a minute. So I'm going to pull these out and say, and keep these over to the side. And I want to talk about 3 facts I think explain why simulation has been so useful historically in science and engineering. So first is the fact that real world processes can be described by equations and models. Okay, and this is not a given, but the fact that we can describe natural phenomena very compactly and use that to make predictions is important. And simulation as a tool translates these equations and models into predictions for us. And again, crucially, the accuracy of the simulation scales with the compute resources that you allocate to it. And that's why all supercomputers basically are simulators, because simulation is something that you can increase the resolution. You can get more accurate predictions by investing more in your memory or your compute, your speed, things like that. I think there's 3 other facts that explain why learned simulation is so promising. So the first is that developing good models and equations, while possible, is costly. You need experts to write down the equations, craft them. To implement the models takes a lot of work, to make the approximations, to get it to actually work on a computer. Learned simulators, by contrast, can translate data, historical data, into predictions. So we can cut out the middleman of going through the equations and the models. And learned simulators can, in principle, be much more compute efficient. So there could be a lot of advantages to learn simulation by basically, as I'll get into, learning the sort of causal processes at a coarser temporal and spatial scale allows you to make similarly accurate predictions, or even better, at a fraction of the compute. And there's a few other bonuses that I'll kind of touch on throughout the talk. It's often easy in machine learning, especially with graph neural networks, as I'll kind of get into, to incorporate physical and other inductive biases about the actual process that you're interested in. And also the fact that we're using neural networks and graph neural networks, they're automatically differentiable, and I'll talk about a little bit of work that's going to exploit the fact that we can differentiate our learned simulators. So here's some background. I'm sure this is probably the last group that I need to give this slide to, but just to kind of, again, establish kind of common language, and so we're all talking about the same thing. So I think everything I'm going to talk about, we're going to use graph neural networks. We're going to use a particular sort of species of graph neural network that my group is always leaning on and very excited about, which we call graph networks. And again, just as a sort of basics, a graph neural network takes a graph as input, and it returns effectively the same graph structure as output, but with primes on the edge, vertex, and maybe global attributes. And these primes are obviously updates at some function. It preserves the structure, but predicts new attributes of the graph. We call it, in the graph network, we call it the edge block, which I'll get into in a second, this node block, and sometimes we use this global block, which we won't really use that much anymore. But the idea here is you're going to compute local sort of interactions, update the nodes, and then maybe even compute global properties of the graph. And I think I'll just probably kind of go through this real quickly. So the edge block, performs learned message passing. So what it does is the edge block, this phi e, takes the input edge attribute, the two vertices that are sending, that's the index S, and receiving, the edge, sending, receiving, and maybe a global attribute. It takes those arguments and it returns an updated edge attribute or a message. And we sweep that function over every edge of the graph. Once we've done that, we compute the node updates. So now the nodes, we aggregate all the incoming messages to each node and make an update using phi v of the node, and that's where the v prime comes from. And I won't even talk about the global block because we don't really use it. And you'll see in almost everything I'm going to talk about, we love this pattern, this encode process decode, where you have some graph network encoder that takes some input graph with some semantically meaningful attributes, embeds it into some latent space where the vertices and the edges have some 500-dimensional latent embeddings, run a bunch of shared or unshared, usually, graph neural network blocks, and then decode that back out to whatever the task demands. Okay, so here's how this works when we start to apply this to learning simulation. So this is a process that involves a fluid, like a cube of fluid splashing in a box. Okay, so these particles here represent the fluid's density, and this is some traditional simulator that is basically stepping forward in time one by one and just making small local updates to the particle positions based on their neighbors. And that simulator is represented by this S function. So a learned simulator just parameterizes this S function with a theta. Okay, so we like to kind of break down the learned simulator into two components. We say the D is like the dynamics part. That's the actual parameterized graph neural network encode process decode thing. The update is usually like, you can just think about this as an integrator. It's going to take some prediction about how stuff is going to move, the dynamics information, and then just update the input state to evolve it in time. And usually we'll just train this with supervised learning, usually one step. At the end, I'll talk about multi-step. But basically the idea is this is going to be a neural network. We're going to just optimize the thetas so that it matches whatever the ground truth, either simulated data generating process or real data generating process would predict on each time step. So breaking this down more, the encoder, in this case, this fluid is represented by particles. These xi's are the positions, velocities, maybe material properties, viscosities of the particles of the fluid. And the encoder does two things. It first, see, it's a little hard to see, but there's this gray circle that is drawn by this laser that's right here. So you're seeing we're introducing edges that connect this particle with the neighbors within some spatial region. And we also introduce edge attributes like the relative displacement vector. that gives more information about how the particle is sort of related to its neighbors. So that's building the graph, and then we embed all of these things, all of the vertex and edge attributes, just using like a parallel sort of independent MLP. Now we've got an encoded graph G0, and then we're just going to run this processor. I think in this case, in this project, this was, I think, 15 times or so with unshared blocks. We have residual connections if you're interested in details. But basically what's happening is that you're passing messages that are communicating information around the sort of, the really 15 hop, M hop neighborhood around this the node. And then it gets, at the end, you have some dynamics information that sort of takes into account its own information and also its neighborhood. And then we just predict out the change in position, the change in velocity or something like that. Usually it's just, the change in velocity, change in position. And then we just use an Euler integrator to update the input state by this delta, and that gives you the next step in time. And so when you do this, you get something like this. So on the left is the ground truth simulation that we use to generate training data. And on the right, you have the rollout from the graph neural network-based learned simulator. And both are initialized at the same input states, like set of particles. And both are kind of rolled out, just taking their own predictions and then feeding them back in as input. And I can't remember how many steps this is. I want to say it's like 500 to 1,000. The reason that you don't see the particles here is just because we've done some like post-processing to make it look fancy, but you're going to see in a second, this sort of smooth surface will dissolve out and you'll see the actual particle representation. There it is. And again, this is just a hallucination of like hundreds of steps of rollout, and it was only trained on one-step predictions. Okay, so that's this is sort of simulating a material that has properties that are analogous to like water. Probably you look at this, you're like, that's kind of like water. This is sand. So this was generated by here. These are 19. I think the last one was 14,000 particles. The smooth particle hydrodynamics was the simulator that generated our data. This is a material point method with 19,000 particles. So this works on different. You can use different simulators to generate the trajectories of training data. This is our goop. This is the technical term for this material. This is just another, it's like higher viscosity sort of material. It's kind of like, it's also material point method. And you can see it's very realistic. Like the rollout of the fluid or the goop looks a lot like what's actually happening in the ground truth simulation. And we can also make more complex scenes where we have like little obstacles and ramps and walls and stuff in the fluid. So these are also particles. They're just annotated. They're labeled in the inputs with an attribute that indicates that they're a solid, and that means that they shouldn't move. And then the fluid particles in blue bounce off of them. And that's just because that's what they're doing over here as well. We can have more complex interactions among the materials in the simulation. So this is actually demonstrating two things. So this is first showing how water and goop and sand can all interact with one another. But also, I'm not showing it, but this was trained on a very small box. Like I think this is, I want to say it's around 40 times as large as the box that was used for training. And we also in training didn't have things like these inflows where like a new material just appears. But because, again, if you remember how the Learn simulator is organized, the locus of learning is local. It's just sort of learning how to update local regions of the particles at local regions of space. And so it doesn't really know about the whole box. I mean, there is, 15 steps of message passing, but it's sort of, it kind of general, it's a convolution all over the graph. You can just at test time, just increase the size of the box and it just sort of works because it never really knows what the large scale global structure of the box is anyway. We can also do, 3D materials where now you got like a rigid that's not, it's not fixed in space, but it's actually like, this is I guess like a particle-based rigid. And again, we just annotate these particles, these green particles with a label that indicates that they're solids. And that means they need to keep their relative positions and orientations with respect to their neighbors. Okay, so that was fluids. So that was a project that we did several years ago and we published in ICML in 2020. This was a year after that. This was in iClear in 2021. We wanted to extend that model from just particle-based fluids to meshes. And the reason for this is that meshes are a representation that's used very widely in numerical methods for solving complex dynamical systems, so fluids, for example. And as I'll show you, this is basically a generalization of the model I just showed you, but it's very, very similar. So the 4 domains we wanted to explore were this cloth, this sort of complex cloth material. You can see the little mesh, we've overlaid the mesh vertices and edges, so you can kind of see its representation. So the structural mechanics thing where you've got these like bars kind of deforming these metal plates. This is a compressible fluid like air and an incompressible fluid like water. So this is like an airfoil, or like a kind of famous ideal scenario and domain in fluid dynamics is this is cylinder flow. You see little like vortices and little sort of structures that are kind of calving off the edge of the cylinder. The model works almost the same way, but there's sort of, now what we've done, we've sort of layered 2 models. So basically we have 2 types of edges. So these world space edges are the same as I described before, where you just look in your local neighborhood and introduce edges among things that are connected in a spatial neighborhood. And then we also have mesh space edges that are given as input. So instead of giving it a set of particles as input, we're giving it a mesh. And those mesh space edges they mean, if it's like a cloth, like don't let these vertices get too far apart from one another. And so we basically have 2 update functions, unshared parameters, message functions, unshared parameters, and those are for the mesh space and the world space edges. But then we just have the mesh space messages and our world space messages that are used to then update the nodes and compute the update. One thing that's interesting about this is that this model is about 10 to 100 times faster than the simulator on which we trained it. The reason is because we are taking much longer time steps. And the reason, again, this is sort of, I think this is a really sort of important point. It's that because it's a neural network, it's a very expressive, rich function approximator. So it doesn't have to kind of stick to these local simple update rules that were used to implement the traditional simulator. Instead, it can learn a function that describes the behavior, the dynamic behavior over a much longer window. And that's where I think, there's a lot of opportunity to gain efficiency and run these things a lot faster with minimal loss in performance. So here's what happens when you train this model. So again, left is the ground truth of the cloth. The right is the predicted dynamics. And again, it's just the input is just the initial state of that. It's like, that's like the input. And then it just hallucinates out by feeding its own predictions back in as input. It says learn remeshing here because we actually have this extra little piece in this project where we train a separate model to predict how to remesh. So in a lot of cloth simulations, they do adaptive remeshing in order to allocate finer resolution in the more complex parts of the mesh. So we trained a model to mimic that. And so actually, if you probably can't see this, but if you look closely, you'd see that this mesh is actually changing on each time step. We're remeshing and coming up. We're like adding new vertices, deleting some vertices, adding new edges to sort of put all the most of your vertices in the regions that need a lot of resolution. Here's the structural mechanics. And again, it just sort of looks like the same on both sides. Here's the compressible and incompressible fluid. So again, this is like air, it's an airfoil. Here the mesh is, the positions of the mesh points are fixed. What we're modeling is the pressure and the velocities of the fluid. So it's pretty good. We also, again, can generalize to more complex shapes than we trained on. So here the training looks something kind of more like this for these ones, but we have 3 flags, and there's the mesh. Here we've got a much larger one than we trained on. You're going to see inset here. So this is the size to scale of the sheet that we trained on. So you can see there's like it's much larger and also has this sort of complicated little tails at the end of the windsock. So that generalization, I mean, I really like this idea of being able to train on something small and high resolution and then generalize to something large more efficiently. Cool. Okay, so that was those are the sort of 2 main sort of like, I guess, background or foundation work for the rest of the talk. The next thing I want to describe is some work we did that we had in NeurIPS this past year. where we took that last model I showed you with the cloths and the structural mechanics and the fluids, not the structural mechanics part, but the really just the fluids and the mesh fluids and the particle fluids. And we wanted to use that as a forward model to solve an inverse design problem. And so the idea there is, like in this example, we want to route this inflow of liquid into these purple buckets. And the way we're going to route it is by deciding on a shape for this green surface. So this green surface, if you look closely, it has these like funny contours, and they cause the fluid to kind of fork and go into these purple buckets. In this simple 2D example, it's hard to see on the screen, but there's like actually, you might be able to see there's sort of this yellow region here. That's like the reward region. So those are playing the role of the purple buckets here. Basically, the idea is create this sort of shape that will cause the fluid to come to rest in this yellow region. And in the airfoil optimization case, we're trying to maximize lift and minimize drag, which is a common sort of objective for good airfoils. Okay, so I thought that was okay, good. In inverse design, some strategies that are commonly used. So black box models that are sample based. So they'll have some forward model and they try out different designs and they sort of have some smart proposal mechanism that tries to pick the next design on the basis of how well the previous designs worked. You could, a very common thing with surrogate modeling in the sort of engineering literature is using gradient-based methods with analytical models. So they'll have like an analytical definition of a forward model with like the gradient, they can compute the gradients, like adjoint methods. And then they backprop gradients through that, and they're going to just do gradient descent, just like you train your neural network by optimizing the objective with respect to the weights. They optimize the objective with respect to the design, like the parameter, like the design, the shape. So we're going to do basically the same thing as this, except we're not going to define by hand an analytical model. We're just going to use our learned model that we trained and just on a forward process. So the question is really, can we backprop error gradients through our learned model where the training was on this kind of stuff and this kind of stuff, and design things that will cause certain scenarios to unfold that we want. So here's how that works. So there's like an inner loop that's the rollout of the forward model. So this is just like what I was showing in the previous pieces of work where you're simulating the fluid forward. But the difference here is now we have this phi which parameterizes the shape of this. So an input is like the fluid state when it comes in, as well as the design, the surface, like that's a height field. So basically red means it's like kind of low and blue means it's high. It's just telling like that's just telling what the shape is. So you're kind of looking at like the sort of topology of this shape from above. And so for a given shape, it's going to cause some outcome. And the outer loop, the design loop, we basically are going to we start with some random initialization of this, and then we're going to make a prediction about what happens. And most of the fluid is not going to go in the purple buckets. And then we're going to take all the error. We're going to compute some error that says how much fluid didn't go in the buckets. And then we're going to optimize this design shape to get more of the fluid to go in the purple buckets. And that's just this design loop. So we're going to have K steps of this. So when we do this, so what you're seeing here, this is these are each 3 different tasks. Here, it's trying to get the fluid to go in the yellow region here. Here, it's trying to get it to go in the yellow region here. And here, the yellow region's over here. But now instead of having like a single ramp that can be deformed, it's like a lot of little ramps that can kind of pivot. And you're not seeing time steps here. What you're seeing is optimization steps. So the first, actually I like this, that's like the initial guess about what the right design is. And it's not very good because most of the fluid does not end in the yellow regions. But I don't think I can stop this halfway through, but over the search, you basically get better and better designs. And at some point, the design really is capturing the fluid. It's coming up with the design that captures the fluid. And this is the sampling-based method that is sort of popular in like this, in robotics control literatures. And so in general, like the results are showing that our model, this GDM gradient descent with a learned model, this blue bar has higher reward than these sampling-based methods, either with a learned model or with a true model. We can also do it so I should say, this is sort of like a lower dimensional problem. Like this has This one I think had 8 or 16 parameters that define this sort of spline shape. This one has whatever it is, 1, 2, 3, 4, 5, 6 times 636. They're just angles. Here, this is like 600 dimensional. So as you increase the dimensionality of the design space, the sampling-based methods have become relatively less efficient. More, gradient descent, obviously, it's 600 parameters. We train neural networks with millions of parameters, right? So gradient descent scales great to high dimensional parameter spaces. And that's why our model is working a lot better than the sampling-based methods here. So, sorry, this is the airfoil. So I won't really get into too much explanation of what this means, but basically we found that when we just train one model and do gradient-based optimization, that's blue, we get reward that's close, like the maximizing lift, minimizing drag, it's close to this like gradient-based design software that we found off the shelf. When we train an ensemble of models, so we basically randomize the model training, the forward model training, and then ensemble their predictions together, we can, with only an ensemble of 5, we can reach the performance of the sort of traditional off-the-shelf design software. Right. So basically, this work is just to show that we can exploit the differentiability of the sort of neural net, the learned simulator to solve inverse problems. Okay. So actually, I wasn't going to show this, but I was. We were having a conversation earlier about physical inductive biases, so I thought I would just throw this slide in because, or this small little piece of work in to kind of show how we can go beyond just kind of this very basic make some dynamics prediction and just update the state. We can actually include more inductive biases drawn from physics. So we called this the Hamiltonian ODE graph network. So this is like my cartoon model of how physics works. So like if there's any physicists in the audience, like I'm sorry. But basically, like you start with some state, this is like the position and momentum at time n, and then it goes into this like physics process, and then out comes the future, n+1 steps later. So, but I think this is actually like fine. Like you can think about, you can treat it as a black box, and you can say that, yeah, like physics is some complicated process that evolves states over time. The stuff that I just described, I'll label this as their forward graph networks. So basically what happens is you take the state, you put it in some graph neural network-based learned simulator, it predicts changes in the state, and then you add those to the input to get the new state. So this is like an Euler integrator. Normally what people do when they're using integrators and solving like ODEs and PDEs is they have some integrator object that calls a function that returns time derivatives of the state. So it's like an initial value problem. You say, here's the position of momentum at time n, and you have a function that can be evaluated, that you can get the time derivatives from different initial conditions. And the integrator might call that once, like Euler just calls that once, but other types of integrators, higher order integrators, more sophisticated integrators can call that multiple times, or can do different, they can make different types of they basically, again, what really happens is the numerical methods community, they do the Taylor approximation, they want some guarantees, they want some properties, and they derive an integrator that will satisfy those things. So there's different integrators for different purposes, but again, long story short, what they're doing is they're saying, take the time derivative function, put it into the integrator, that's going to call this a bunch of times and then update the state. So this is like, normally this is again how physics would, if you represented physics, the state of the graph, and here's the positions, here's your time derivatives, and that here's your time derivative function, and there's the actual instantaneous time derivatives. That's the thing that the integrator will call several times to update. So we introduced what we called first just an ODE graph network. And the idea here is that the time derivative function is going to be a learned function that's represented by a graph neural network. And so what we do is we don't train it with just a plus, we train it with some other integrator. And we have a function that's a neural network that just predicts the instantaneous derivatives, and then the integrator function. Most integrators are differentiable. So you can backprop gradients and just do one-step supervised learning, just like I've been talking about. And you can update this instantaneous time derivative function. So again, the difference here is this thing is predicting a change in position and momentum. This is predicting the instantaneous time derivatives of position and momentum. But where we bring the physical inductive biases are in, we can get a little bit fancier. So what we can do is we can say, well, there's other formulations of mechanics that we can exploit, and we can learn different we can approximately learn different functions that will then play key roles in those mechanics formalisms. So what I mean by that is, in Hamiltonian mechanics, the time derivatives are defined as the partial derivative of the Hamiltonian, which is a scalar function, the partial derivative of the Hamiltonian with respect to the momentum and position negated. So basically what we're doing is our neural network is not predicting some positions and momentums or instantaneous time derivatives at all points in a graph. Instead, it's predicting a single scalar for the graph. And then we compute using auto differentiation in JAX or TensorFlow or PyTorch or whatever. We compute the partial derivatives with respect to the inputs in order to expose those time derivatives. So what we're doing here is we're basically saying we're going to use Hamiltonian mechanics as our formulation of dynamics, and we're going to learn the dynamics in the form of a scalar Hamiltonian, and then we're just going to use Hamilton's equations to get the time derivatives, and then we're going to use the integrator to get the update. And this whole thing is differentiable again, so we can backprop error gradients through this whole thing and learn a Hamiltonian. And the reason you want to do that is because different mechanics formalisms have different trade-offs. So the Hamiltonian, for example, is well, it often represents the total energy of the system. And if you use a symplectic integrator, you're going to preserve energy and you're going to be time reversible. So you can get sort of benefits of this that you wouldn't necessarily be able to get from formulations like this. I should also point out this is similar to Sam Gradanis' 2020 Hamiltonian neural networks paper that was sort of parallel work. So here's an example of why this is kind of helpful. So here's some particle system that's ground truth particle system. What I've done is I just pulled out the blue particle here to show you what happens. So this is like if we integrate the true Hamiltonian of the system, and you see that the red is like the simulated trajectory, which is perfectly overlaid with the blue particle. So you can't even see that there's a red. The blue is hidden, but there's two particles here. This is the forward graph network style thing that I was showing before, where over many, many steps, eventually there's some decoherence, and the predictions in red differ from the ground truth in blue. But if you model the time derivatives directly, we were finding that you can actually get more coherent systems over time. And when you model the system with the Hamiltonian, you can get even more coherent predictions over time. And to show another sort of benefit of this, I think in the interest of time, I'll probably just show you this one. Because we're learning the instantaneous time derivatives with our ODE graph network or our Hamiltonian, we can train with one time step and test and generalize to other time steps of the integrator. So you can train with either long time steps or short time steps within reason, and you can basically generalize well. So the blue is the forward graph network that's just using the fixed time step. And this is like the evaluation error, and this is the time step on the x-axis that it was trained on. The only one where it's doing well, low error, is the time step it was trained on. You can't see, but there's actually like this little gray region that shows the time step it was trained on. But the Hamiltonian and the ODE graph network do well on a lot of time steps that they weren't trained on. And when we increase the time step that the range of time steps that the model was trained on here, again, you can't see it, but the region, you have to believe me, the region is basically like this. The forward graph neural network simulator does well on those time steps it was trained on, but not on other ones. So this is again showing that we can generalize, again, we can sort of exploit the fact that that once we learn the time derivatives, we can integrate them with any time step and get, generalized to different time steps than we trained on. So for example, if your data came in at different time steps than you actually want to integrate on, you could do that with this type of method. Cool. Okay, so for the last 15 minutes or so, 10 minutes, I'm going to talk about some work that we did very recently on learning weather forecasting. So the reason we started doing this work was because with all the stuff I've shown you before, it was like, take some simulator, generate some training data, train a neural network to simulate that simulator, but like we already had a simulator for it. Like we're not going to do any better than the simulator that we trained on. The only hope is that we can be more efficient. And we did show that we can be more efficient, but the real thing that we want to do is start to learn better simulations than any simulator in the world that exists for an important process. So again, the work that I showed at the beginning was more kind of proof of concept that like these types of methods can increasingly simulate complex physics, and we sort of convinced ourselves of that, and learn lots of tricks and sort of lessons along the way to get better and better. And now the goal is to put our methods to the test in a more complex real-world problem. Now in weather, we do have good numerical weather predictions. So the question here is, can we outperform those numerical weather simulations that they use to generate the weather forecast that you have on your phone? And we want to see if we can be more accurate and also faster. Okay, so the problem statement here. So what we do is so current numerical weather prediction systems, they're complex and expensive. It is a triumph of modern sort of science and engineering, how the fact that we can know the weather like 10 or 15 days in advance to some degree of accuracy. I mean, this is like, if you told someone this, hundreds of years ago, they would just think you're crazy. And we're talking about a chaotic process that's interacts at a global scale. It's nuts. But they're still expensive to run and to build. These are the types of things that we want to predict. So this is the Earth. This is surface wind. This is surface temperature. This is temperature up in the atmosphere. You'll see this a lot, this hectopascals. In meteorology, they often don't use like physical distance to measure altitude. They use pressure levels. So it's like they say, at what height was the pressure 50 hectopascals? Hectopascals are a measure of pressure. The temperature at that pressure level is sort of more meaningful. These are 3 examples of the 227 weather layers that are in our data set that we're going to model. Okay, and so one thing I have to explain to start with is what the baseline, where the data comes from, and what the baseline model is. So ECMWF is the European Center for Medium Range Weather Forecasts, and they generally are considered to produce the most accurate operational global weather forecast in the world. Again, the weather app on your phone, there's a good chance that it's it's probably like some weather company has taken the ECMWF forecast and maybe a few others and tried to create an even slightly better forecast, but basically it's rooted in this source forecast. Our goal is to beat ECMWF's high resolution deterministic forecast, HRES, and we're going to operate at 1/4 degree latitude longitude resolution, 10-day forecasts, 4 times a day, 6-hour increments at 37 vertical levels in the atmosphere. So here's the model that we use. It's going to look pretty familiar. We basically take the state of the weather, we represent it on a latitude longitude grid that has, it's sort of a 2D sphere, and each point on the grid represents the surface variables as well as the variables up into the atmosphere. And we're going to put it into a learned simulator, that state of the weather. I should say, you can see like the little yellow here indicates like surface variables, and this is like the blue is the atmospheric variables. And if you look very closely, you'll see the blue, the little like dark blue to light blue kind of repeats, because we have 6 variables at each of 37 levels. So it's like repeating the same variables as you go up into the atmosphere. I'll describe the variables in a second a little bit more. So you put it in the learned simulator, you're going to run it, and you're going to make a prediction of the next weather state 6 hours ahead. You're going to feed that back into itself, and you're going to iterate. Here we take 2 frames of weather states as input and just make 1-step prediction. The way that works, again, you have this encode, process, decode pattern that we always use. So here, the latitude longitude grid runs through an encoder, which is a set of directed edges that go up to what we call multi-mesh representation, which I'll describe in a second. The processor is, in this case, it was 16 steps of unshared message passing over this multi-mesh that's used to sort of propagate information and form the computations that try to capture the dynamics. And then we decode the representation at each of these multi-mesh nodes back down to the latitude longitude grid. This multi-mesh, so what is it? So what it is a union of 7 icosahedral meshes. So what does that mean? So icosahedral mesh, so this is a base mesh that is very, very coarse. So you can see there's, what is it? Icosahedral, is the 20 sides or 20, I think it's 20 sides. I can't remember now. Then what we do is we basically take each face of this like base icosahedron, and we split each edge and introduce a new vertex here, here, and here. And then if you look here, so that was that like base triangle. And then you've got new ones here, 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 and those are used to form a new face, actually 4 new faces. And we keep doing that successively until we've iteratively split those edges 6 times. And then that forms a total of 7 meshes. And then we basically just take all of those edges and nodes, and we just make one big graph. And that graph kind of looks like this. So you can kind of see there's like long range edges and short range edges. And this allows us to capture local fine resolution information as well as long range spatial dependencies. Yeah, I think just to point out, there's 40,000 nodes and 300,000 edges roughly. I think we're up to, I think, M7 or 8 now, so we're quite a bit higher now in our internal stuff. Some more details. So this is the latitude longitude resolution is quarter degree, like I said. So that means there's about 1 million points across the Earth, vertices across the Earth. On the surface, we have 4 surface variables: temperature at 2 meters, the U and like the kind of latitude and longitude components of the horizontal wind speed, and the mean sea level pressure. For the atmosphere, we actually have precipitation too, but I'm not going to talk about that at all. So you can ignore it. We actually have 6 atmospheric variables, but we only actually evaluate on 5 of them, and we're kind of getting rid of the 6th one because we don't think we need it. But basically, the atmospheric variables at each of 37 vertical pressure levels: temperature, the wind speed, specific humidity, and then geopotential is the height of that pressure level. So if it's a low pressure system, then the height is going to be that's relatively high, I guess, right? Or no, low, right? Yes, low pressure system. So 500 hectopascals, or whatever hectopascals you are, the Z is what vertical height that pressure level exists at. 10-day forecast at 6-hour increments, and we're going to initialize them daily at 0, 6, 12, and 18 Zulu. And just some details on how we train, how it runs. So the input state is huge. It's like each frame is 950 megabytes. So the 2 frames of input for each step is like 1.9 gigabytes, which is enormous. The whole 10-day rollout is 38 gigabytes. So like already this is like a huge engineering headache to even get this to fit on hardware. We think this is probably one of the largest input output memory footprints that are used in ML. We don't know. If anyone knows anything bigger, let us know. The architecture, to be specific, so we have 1 input embedder, 1 encoder, GNN, 16 unshared message passing graph neural networks, 1 decoder, and the latent sizes we use are 512 dimensional vectors, squish activation layer norm. In total, it's about 36 million parameters, which is actually tiny. It's like smaller than AlexNet. We can't, if we had more parameters, that would mean we'd have more activations, which means we'd have more memory footprint, which means we wouldn't be able to fit it on a computer. So that's why we have to make it that small. And the data we trained it on was 35 terabytes of historical weather observations from the last 40 years of Earth. So there's ECMWF has global weather everywhere on Earth at 0.25 degree resolution. And we just use that as training data. So now that, instead of a simulator, that's our trajectory that we're going to cut up and do supervised learning on. We also often do 12 autoregressive steps of backward. So instead of predicting 1 step, we often predict 1 and then feed that back into itself and do it 12 times and then back propagate gradients through all of that. But that's not that important. Speed, it takes about 3 weeks to train on 32 cloud TPU devices. And the inference time is about 60 seconds on 1 TPU. By contrast, the HRES system that ECMWF has built takes about an hour to run on a 11,000 core cluster, but it's higher resolution, but it's much more compute. So we don't really know how to do the apples to apples comparison, but we think we're pretty competitive speed-wise. One other bit, I'm running out of time, so I'll just kind of like just give a very quick summary of this. We were very, very careful to only develop the model and do all of our like prototyping and training on data that came before 2017. This was held out for validation. And then we actually didn't even run our test evaluation until we had completely frozen them. We were happy with the model and we froze it. And then we ran our tests. Whether, like we just didn't want to have sort of like there's not that much data. We can't just generate more data. So we want to be really careful not to make choices about the model that were biased by looking at the test set, and weather data is sort of finite. Like you have to kind of wait for more weather to happen. So we want to be really careful not to kind of like look at the data and then have it contaminate our choices. So here's what happens after you train. So HRES is the top row. GraphCast forecast, 10-day forecast is the bottom row. These are just like errors between the forecast and the ground truth. So this is the forecast, and you can see it looks like weather, which is good. If you look really closely, you'll notice that, and you can integrate spatially with your eyes, you'll notice that there's actually like slightly lower error in our forecast than in the operational forecast, which I'll show you in a second. But also just to kind of blow it up. So this is specific humidity is one of the highest highest spatial frequency fields. So you can just see this is like 2 days, this is 6 days, and this is 10 days. And you can see that our forecast is like preserving a lot of the fine grained structure in the weather. You can actually, it looks better on my computer. I think that the projector is washing out some of the details down here. I won't get into this. I'll just say that we had to kind of be very careful about how we evaluate in order to make things sort of apple to apples against the operational system. But I'll just show you the results. So the blue line is always going to be our model, the GraphCast model, and the black line is the performance of the HRES operational system. The x-axis is the lead time, like so you make the forecast here, and then this is like the 10-day forecast. On the y-axis, you have the error is the RMSE, so lower is better. And you can see across all lead times, GraphCast has lower RMSE than HRES, which is good. This variable that we're showing is geopotential at 500, which is very significant for meteorological applications. So they often use this in the weather community as like a sort of diagnostic, but I'll show you all the variables in the next slide. This is just the same thing as over here, but just the relative difference. So now I'm just basically normalizing the black to 0, and I'm looking at the improvement of GraphCast over the operational system. The reason there's this like line here was the thing that I just glossed over. It's a little hard to explain, but basically we're evaluating against a slightly, this is GraphCast initialized at 6 and 18 Zulu always, but HRES only has a 3.5 day forecast on those initialization times. So we have to use its 0 and 12 Zulu forecast. It doesn't make a difference. We're actually being kind of conservative because HRES is slightly more accurate from its other forecasts, which is why our like relative improvement kind of gets a little bit worse, but this isn't that important. And then this is just another measure of accuracy, which is called anomaly correlation coefficient, which is just emphasizing it's like sort of a metric that pays closer attention to the deviations from average weather. So are you capturing the differences from normal weather better? And we are. And so higher is better here, and we're doing better. Okay. Oh no, this is like totally washed out. Oh well. So here's a summary of all of our results. So this, I just showed you one variable at one pressure level. This is every variable we model at every pressure level we model, all 37. And so even though you can't see in the projector, most of these things are actually pretty bright blue, which means that GraphCast has outperformed the HRES system at this lead time and that pressure level and this variable. The only exceptions are, I think, right here, I think we're losing to HRES, and then up in the highest vertical levels in the stratosphere, we're losing to HRES. We don't know why this is. We don't really trust the stratosphere data that much. We noticed we've done some analyses that have shown that actually the error is isolated to the stratosphere, even when the stratosphere's height sort of changes. So we think it might be either the data or something funny in the stratosphere, but the stratosphere doesn't really affect day-to-day weather anyway, so we don't really care that much. But anyway, we beat HRES on 90% of the targets, the 1,300 targets that we measured. This is the comparison of GraphCast to the best previous machine learning based weather forecast, and we beat it on 99% of the targets. So this was Huawei's Pangu weather paper that came out a month before we put ours on archive in November. Blue is our model, red is the Pangu weather one, and black is HRES. So we're sort of consistently outperforming the other ML baselines. And one other thing, this is I think my last results slide before my conclusion. There's one thing that's kind of interesting, which is I mentioned before that now instead of doing the one-step training, we train on 12 autoregressive steps. We found this made a big difference. So the dark blue is when we train on 12 autoregressive steps. And then you can see, if you kind of look closely, it gets lighter and lighter and lighter as you go up. I don't know what happened to the HRES line, I guess. Performance that's actually much worse. If you train on 12 autoregressive steps or even like 10 or 8, you do much better. We could talk about this if anyone's interested afterwards. Basically, we think that the we think that this is partly a consequence that we're training with MSE. The predictive uncertainty, the forecast, we only get partly like sort of impoverished observations that you seed your simulation on. There's inherent uncertainty. RMSE says that you should sort of blur out the spatial predictions. So we think that by optimizing over a much longer horizon, we're sort of like gaming the system. So we don't know if this is actually a good thing that more autoregressive training improves our performance, but it definitely improves it on the RMSE metric against HRES. So we can, you can, ideally what I would like is for us to only be able to train on one step because we know the weather. You don't have to, you can just make the prediction about the next step and the weather's stationary in time, but that's the next project. So, okay, so that's it. So, and going back to the thing, my setup, there's 3 facts that explain why learned simulation is so promising. And hopefully I've given some argument that this is the case. Developing good equations and models is costly. So what we're learned simulators, I'm showing you classes of models that are pretty similar to one another, that are simulating everything from fluids in a box to goop to, airfoils and structural mechanics and weather, kind of the same models. So the cost has gotten very cheap for us to develop these things. The learned simulators can translate the data into predictions, like in weather, for example. We had 40 years of weather, but none of us had any real background in weather modeling, but we were able to outperform the operational system because we had the data. In what we're seeing in the weather and the mesh GraphNet stuff is we're much more compute efficient than the traditional engines. So that's it. So, oh, there were some videos. Yeah, this is a sort of way of reminding you what the videos look like. Those are the results, and that's it. So thank you very much.
Thank you very much. Question? Yeah.
So thank you very much for the excellent talk. So you might know my colleague Joey Teran, who does a lot of simulation of the material and so forth, and he contributes to Disney's movies, animation, and so forth. And he basically does, generates training data set in your case, like from first principle, solving PDEs and so forth, and then generate all these nice, animations, movies. And then I'm sure, using your technique, based on those sequences he generates, you can learn or simulate what he generated. So my question is really more like an inverse problem, in the sense that in order to generate those simulate training data sets, well, one needs to basically set up something like a material parameters and all these, things to do the simulation. And then if your, graph neural network basically can, simulate those sequences very well, that must have captured some physics of this simulation. And then whether you can basically get this something like that to contribute to the inverse problem, in the sense that whether from your learned network parameters and structures, whether you can infer something like that, material parameters or some parameters, of the, which draw the PD.
Yeah, so I didn't show this, but I think I have an extra slide here somewhere. Let's see. Yeah, I do. Okay, good. So we did this project where I can get there. Oh, yes, I just have to. Oh wait, you know what? I have to break this. Okay. Yeah, so we did this project where we learned to simulate orbital dynamics, and we included a learnable parameter that was a scalar that basically was basically playing the role of mass in force equals ma, and so we were able to infer the masses of all the planets and moons. Well, estimate the masses of all the planets and moons in the solar system from this. So just because we set up the inductive bias again, that the accelerations were going to be scaled by a scalar. So we assumed force equals ma, the acceleration is going to be scaled by a scalar. Then that scalar has the semantics of mass. So I guess what I would say is if I think the answer to your question is there's not, like, when you just look at the sort of neural networks, like there's nothing, somewhere in the representation must know about material properties, but we don't know how to get that out unless we include an inductive bias that basically gives it a dedicated role that like sort of specifies what it is. So this is the only example I can sort of think of this, but again, for it to distinguish between, you know, water and goop, it must know what viscosity and stuff is, but we don't know how to get that out unless.
Because I think it's important to give some feedback to those modelers and the simulators. For example, in the this Earth temperature environment simulation you showed in the end. For example, we know that you need this other simulators based on some NPV and so forth. But then if you can point out, so here is the things you should change or modify your equations or simulate.
We don't need equations.
That would be really.
But we don't need equations anymore. We have data. We don't need equations.
Yeah, but then people still may want to understand data generating mechanism.
So we did. I should also, maybe in this one, we did actually. The second part of that mass project was doing symbolic regression to get out a symbolic form for the laws of like the force laws, basically. But again, this was more just, this isn't going to really describe it, but you can see we're getting out an expression that looks a lot like Newton's law of universal gravitation, which we confirm it is. But again, like there's a question of like, why do you need the equation? So I can think of some examples, like equations are real fast. Like a neural network is kind of slow to run, but an equation is very fast. Another thing is we can study like the solar system, model the solar system, and then predict what's going to happen like in galaxies because gravity applies to both. So equations can generalize well and can be very efficient. They can also maybe like it's a nice language for connecting to other pieces of knowledge that is expressed as equations. But in some sense, like you don't necessarily. You want to, in my view, you want to always know why you want the equations and why you want to improve the equations or the approximations that are for the numerical methods before just sort of like, oh, you want that interpretability. Like maybe you don't, because for a lot of things you don't. You just need to know, like, is it going to flood or is it going to be a heat wave? And the equations don't matter. It just to people they just care about if it's going to flood, right?
Thank you.
Yeah, I have a question. So when you have a physical system and you make a mistake in your prediction, this mistake, just any prediction increases with time. And this means that at some point you're going to have conditions that are not physical, for example, right? In physical systems, like the one that you're. So from a practitioner perspective, how do you keep your physical system in the physical world? Do you project after the prediction? Or do you do some like batch normalization, some physical magnitude that needs to be preserved or something?
Yeah, I love this question. So the way I think about this is there's sort of three types of constraints, like three general types of constraints. One is like what is a plausible physical state, period. So for example, like if you have I have negative mass, not physical. Right. If you predict, I don't know why you predict mass, but if you can predict things that, were faster than the speed of light. Velocity is faster than the speed of light. Nope, not physical. So that's like, I would say like a 0th order constraint. Nothing can violate this. Then there's like trajectory specific constraints. So if you start a ball in one box and it's like a closed box, it can never go into a different box. It's like staying in that box. You just, once you know it's been in that box, it stays in that box. You don't have to know the immediate preceding time step. You just need to know any other time step to know it's staying in a box. And then that would be like the first order. The second order maybe is the temporal sort of local temporal contingency that like it's, if it's here and it's moving this way, it's going to keep moving this way. So I think that the answer to your question, I think this is a really important thing. So I think that with, we have generative models, like there's all sorts of, generative AI and diffusion models and things like that are we're really good at modeling this sort of marginal and conditional distributions of data. So one idea is just to push states that start to kind of misbehave back onto the manifold of things that satisfy one of these constraints. Because like in some sense, what we're only doing is really just modeling the temporal contingency and hoping that the other stuff sort of works out, which it kind of should, but you could imagine more explicit ways of basically just saying, this has to stay on the, in the physically real thing, or the, on the trajectory in the phase space, or even the thing that's, that sort of satisfy the constraints that are local in time. But I think we haven't done this, but it'd be really great to study like generative models to nudge things back onto what's probable.
Yeah, at the resolution of 25 to 35, I guess you used a lot of local very important true or not. Second question is, since now you have this simulator which you use to produce, with all the data that is being measured, is there any plan or chance of doing data simulation to improve your prediction?
That was a good question. So the first one, yeah, I mean, like I think Tim Palmer gave us a talk like early last year, and the climate scientists, weather scientists know this, that like we need probably so ours is 25 kilometer at the equator. The HRES system is 10 kilometers at the equator. We need like 10 meters, maybe 100 meters to resolve clouds to really get the, because clouds are really influential in determining the weather dynamics, and like we're decades away from having to compute for that. So yeah, so we need better observations. I actually wonder whether some of this stuff with like learning simulation will push to get better observations, because we know the value of the data can potentially be exploited. So maybe we get finer resolution observations. But yeah, like we need much higher resolution, but you can kind of think about this as like a kind of subgrid process, right? It's like a subgrid process. Like we're operating a coarse scale, but we're modeling this sort of subscale effects to the extent that it's sort of possible. The second question about data assimilation. Yeah. So data assimilation for everybody, it's basically the process of, so what we're doing is we're initializing from a state of the weather, making a forecast. Data assimilation is taking observations and inferring the current state of the weather. And in meteorology, data assimilation is about half of the sort of cost and compute and probably money, is just taking all the observations, making an inference about the current dense sort of representation of the atmospheric fluid. They often use numerical weather models to do data assimilation by solving an inverse problem that's like what weather trajectory would give rise to these observations. And they often use gradient-based, they approximate the gradients of the numerical method. So again, we're definitely thinking about this. Like, can we differentiate our models to do, to optimize for the weather state that would have given rise to the observations? But we haven't done this yet. But yeah, observations are hard to come by. They're sort of like it's kind of political, because there's like the governments kind of hold them in their secret satellites that are taking pictures of the Earth, and it's sort of tricky. My understanding. Yeah.
Okay, maybe we take other questions offline because I don't want to feel completely like a break. I think we stay not too long, so if you have questions, maybe try to push it. Otherwise, we'll have to go.